all along the ocean, and it forms this really formidable chain of underwater volcanoes. And you know, it's where oceanic crust is being formed, and it's a very important part of crustal formation on Earth. So how do we get this oceanic crust to form? Oh, I have this. Right, so the classical view of creating this volcanism and melting is by decompression melting. As two plates move, is being pulled apart at the top, this causes mantle upwelling, so here. And that the melt generated by this process then forms the oceanic crust. So as you can, all of you probably know about plate tectonics, there's plates that's moving on top of the mantle, and they all move at very different rates. And so that would cause the mid-ocean ridge to pull apart at very different rates. So at the fastest, you have sparing rates about 15 centimeters per year at East Pacific rise, and then you have slowest of 0.5 centimeters per year at Gecko Ridge up in the Arctic. So when you see that there's so many different spreading rates, you might think that there's a lot of parameters that is associated to this varying spreading rate. So one of the most important observations at mid-ocean ridges is the oceanic crustal thickness. And that's usually observed by geophysical surveys. So the plot here is one of crustal thicknesses and half spreading rate on the x-axis. So you can see that below 1 centimeters per year, there's kind of a increase, very sudden increase of crustal thickness. And then beyond that, it's kind of stagnant at about 6.5 kilometers. And this is all based on seismic observations. And so regardless, and you have to remember, most of mid-ocean ridges has a half spreading rate of more than 1 centimeters per year. So most of mid-ocean ridge lays in this region. And all of them form, if you can think what they are like, this 7 kilometers consists of the Pilo lava, sheeted dike complex, gabbro, layered gabbro, and then you have the moho and then the upper mantle. So another really interesting thing is that the oceanic crust is formed within a few kilometers of the ridge axis, regardless of spreading rate. So for a slow spreading rate like the Gecko Ridge, it has the axial low. And then for East Pacific rise, where it's much faster, you have an axial high. But all of the all of the oceanic crust is formed really within a few kilometers of that ridge axis. So you might think that most of the melt are generated within that few kilometers beneath the ridge axis. But in fact, that's not what is observed by geophysical surveys. So on the left here, you have a seismic survey. Let me see. So really what is showing us is that based on seismic observation, there's a really wide area of melt that's generated beneath the crust. So it's not just a few kilometers beneath the ridge. And it's not just by seismic evidence, it's also by magnetotelluric survey. So it's showing a really high conductivity area that is interpreted as a white region of melt. So this is a little bit strange. You have a white region of melt, but it's forming crust at a very small region. So you might wonder, how does that work? You have to have melt moving inwards. And so people have thought about this for quite a while. And there's been a few mechanisms that's been proposed on melt focusing. So one of them is ridge suction. So you can think about it as when you pull two ridges apart, there's a suction in the middle where it's trying to fill in the gap. So that's a very straightforward way of thinking about it. And then another commonly invoked mechanism is decompaction layers. So you have to remember that when melt is formed in this wide region, it's buoyant, it moves up, and it encounters a cold and strong plate. And so it starts to freeze into this cold, strong plate, and some of it doesn't freeze and move along this, what we call decompaction layer, because the mantle has to decompact in order to open up pore space for the melt to move along. And that's moving towards the ridge axis because of this slope from the temperature gradient. So by the end of this talk, or at least end of this section, I hope to convince you that we actually see another mechanism from using this melt and mantle dynamics. And so what I was describing before was that's been seen in a lot of models is this ridge suction effect, which is labeled 3, and then a decompaction layer effect on the sides. And what I'm seeing in my models and in more recent modeling efforts is this what we call melting pressure focusing, where melt is focused pretty deep in the melting region, even before it reaches the lithosphere. So the outline of my talk is I've given you the introduction of at least the mid-ocean ridge part. I'm going to talk more about melt dynamics in the mantle, go through some equations, because equations are what I solve. They are very important for understanding all these mechanisms that we observe in the world. And I'm going to talk more about the results for melt focusing beneath mid-ocean ridges. And then I'm going to talk a little bit about the carbon fluxes at subduction zone, which is what I'm doing here if I have time. So we'll see. So usually in geodynamics, we solve for Stokes flow in a single phase. We conserve mass, momentum, and energy, and but then in two-phase flow, we have two different fluid of very different viscosity. So we need to resolve them, and a way of doing this is to conserve mass, momentum, and energy in both the solid phase and the fluid phase. So the next slide is going to be a little bit busy. So these are all the equations that I solve for. So you have the solid mass conservation, fluid mass conservation. The rhos are the density, S are for solids. And porosity is phi. And then you have conservation of momentum. So this is basically the Stokes. And you have the fluid conservation of momentum and the energy conservation equation. But I really don't want you to focus too much on the equations. I just want you to focus on just one, which is the Darcy's equation, which tells you about how melt segregate in a two-phase flow medium. So this is pretty much, this is the porosity, which is the volume fraction of melt. And then VF is the melt velocity. Vs is the solid velocity. K is the permeability of the solid. So you can think about it as, if you have a whole bunch of, so the voids are grains, and the red and the gray are porous spaces where melt is going through. So you can think about how permeability is what determines, a grain from here moving, the east of the grain here moving to the other side of this cube. And then mu here is the fluid viscosity. And then you have the gradient of fluid pressure and then a hydrostatic pressure. So melt in the mantle is really determined by how, the dynamics at least, is determined by how permeable the mantle is when you start melting, at least. So there's been quite a number of experiments that's been done to figure out just how permeable the mantle is when you melt it. So here is a figure from this paper, Zhu et al. So this is a cube of olivine basalt grain aggregates. And like the other picture I've shown before, the void is the solid grains, and the gray and the red are the melt. So A, B, C, and D are what happens when you increase the amount of melt. So A is 0.02, B is 0.05, this is 0.1, and this is 0.2 melt, so 20% melt. So even you can see that the point here is that even at very low melt percentage, the pores are very interconnected. So it's pretty permeable. So melt is moving once you start melting it. So now that we know melt moves, we have to figure out why it moves. And these two-phase flow equations are very complicated, and to try to understand how melt actually moves, we need to figure out what are the pressure gradients that's making it move. So what we try to do is to do a pressure decomposition where this is the total fluid pressure, and it's decomposed into the compaction pressure, the lithostatic pressure, and the dynamic pressure. So the lithostatic pressure is just how much stuff is on top of it. And then the dynamic pressure is, you can think about it as when two plates move, it's being pulled apart, the dynamic pressure would be, the strongest at the ridge axis, where it's trying to suck in the melt. And this compaction pressure is defined here. So it's pretty much the compaction and decompaction of the solid matrix. So you can think of that as, if I'm expanding, I'm creating pore spaces that allows melt to move through. And it's scaled by the bulk viscosity, which is pretty much how resistant is the solid mantle in resisting this expansion and contraction when melt wants to come through. So when you put the pressure decomposition back into the Darcy's equation, what you have is that melt segregation is pretty much because of these different pressure gradients. So you have the compaction pressure gradient and the dynamic pressure gradient, and pretty much a buoyancy flux. So now I'm going to actually solve the equation. I solved the equations in non-dimensional form, and they are finite element in discretized in finite element space and finite difference in time. So at the top of my rectangular domain, this is the ridge axis. And then at the top, half spreading rate is imposed on both sides, so it's pulling apart at the top. And the mantle upwelling is imposed here, and I have an outflow boundary on the sides. And you can see all these little triangles. That's how I'm discretizing my rectangular domain. It is important to try to resolve the ridge axis, because there's a lot of gradients there that needs to be resolved finer scale. And to save computational time, this scale, the triangles get bigger as you go away from the ridge axis. And what I use here is terra firma, which is the transparent finite element rapid model assembler. And this uses open source libraries like PETC, Phoenix, and other things like that, which I can talk about more if anyone's interested. No. Because it's a really interesting question because that saves computational time, right? But sometimes I do see asymmetric patterns. So I'm not trying to say that this is absolutely symmetric. And you can also have Haas-Varying rates that's different on both sides. So this is, I guess, in preparation for future work. So it's nice to know that, okay, even from Haas-Varying rates that's like the same, what do you see? Right. Well, yeah, if your Haas-Varying rate is the same and like all your conditions are the same, yeah. I mean, you can imagine, imposing different boundaries on the side too. That makes it different as well. So, okay, so that's my numerical setup. So let's go to the models themselves. So I want to show you a video, but before I do that, I just want to go through very quickly what it's going to roughly look like. So for an intermediate spreading rate of 4 centimeters per year, you have there's lines. That's kind of hard to see, I realize. That's the melt flow line. So this follows melt. And there's the contours in the center. And that's the melting rate contours. So pretty much what's happening here is like melting is highest in the middle. And that's kind of expected because that's where you have the highest upwelling velocities. And the velocity, the temperature contours are not actually here, but you see it in the video. There's orange contours of 750, 950, and I think 1150 degrees centigrade. So here is an example of intermediate spreading rate. I hope this works. So what you see is this transient that's evolving. And this is very slow, so I'm going to speed it up a little bit. This is non-dimensional time. It's about, 1 unit is about 25,000 years. Oh, I'm sorry. Yeah, great question. It's 200 kilometers and 100 kilometers depth. So you can see where this porosity is. This is about 60 kilometers when it's the dry, the mantle upwelling hits the dry solidus and it starts melting. And so porosity here is about what, 10%. And so this is going through a transient that's a little bit slow here. So I'm going to speed it up a little bit. But you can see that after 10 non-dimensional units, this is just the same thing for a long time. Doesn't really change. It's going to a pseudo steady state pretty much. So this is to convince you that the models seem to be working, and even if I go further, it's fine. So to look at all the different what's going on in the models, you can see from the previous video that you have, so this is for a Haas-Varying of 4 centimeters per year. And so you have high melting, high porosity in the middle, and also high porosity on these wings. But what is kind of a little bit hard to see here is that there's some porosity here. So there's melt being generated all around this region beneath the mid-ocean ridge. And what I want to show here is the horizontal fluid velocity. So this is actually pulling in melt from away of the axis towards the ridge axis. And so remember, this is because of the different pressure gradients, right? How melt actually moves. So when melt is generated in this very wide region, the first thing it does is move up because it's more buoyant than the surrounding mantle. But what moves it horizontally, focuses it towards the ridge axis, is two other pressure gradients, which is the dynamic pressure gradient, where you have that pressure gradient when two plates are pulling apart, and also compaction pressure, which is the compaction and decompaction of the solid mantle, scaled by the bulk viscosity, which is the resistance to this compaction and decompaction. So you can see here that compaction pressure is pretty negative here, so it's pulling in melt, sucking melt towards the ridge axis. And then this is the bulk viscosity, where you have, so it's less resistance to compacting and decompacting in the melting region. And that's because it's actually a function of shear viscosity and porosity. Yeah, I'll get to that. Well, I can also explain it here, I guess. Well, maybe it's clear in the next one. So in this model suite, I've ran 6 models here. So the top row is 2 centimeters per year house spreading rate. Second row is 4 centimeters per year. And last row is 8 centimeters per year. So I've said that the bulk viscosity is pretty important in determining how the solid mantle actually compacts and decompacts to allow melt through. So what I've done is to hold the bulk viscosity constant as 1 on the left-hand side, and then increase it by about 15 on the right-hand side. So what you can see is that, okay, on the left-hand side, it's roughly very similar. You have some melt that's in the center, but a lot of the melt are on these wings. So Connell, to answer your question, most of the melt moves up buoyantly. It's buoyantly rising, right? And then when it encounters the cold, strong lithosphere, it starts to freeze in, and it creates this decompaction layer. And because it's sloping, because of the temperature contours, it's going to move towards the ridge axis. So really, if melt was segregating faster, maybe that would be gone. So we are getting a bit of pooling beneath the, I guess, yeah, lithosphere, asthenosphere boundary.
So regard to lithosphere, asthenosphere boundary.
That's solved for. So if you look. Yeah, so yeah, the top.
Thickness is much greater than the bottom there is much thinner.
Right, and that's because of the spreading rate. So you can imagine, so this is very similar. Yeah, exactly. Yeah. So on the right, where you have a higher bulk viscosity constant, you have more melt in the center, right beneath the ridge axis. So right where the highest melting rates are. And then you have this kind of lobe of melting on the side. So the difference here between the two is that a lot of, if you look at the melt flow lines, most of the melt flow lines are vertical on this side. And it's mainly focused by what we call decompaction layer. And on the right here, if you notice the melt flow lines, I realize it's quite difficult to see this. So I can, a lot of lines are kind of following this gradient towards where it's melting the most, and then it's moving up to the ridge axis. And away from it at about 40, 50 kilometers from the ridge axis, you have melt flow lines that's moving up and then moving to the side. So that's where there's some pooling of melt before it freezes back into the lithosphere or moving out of the domain. So this is interesting. We see that when you have higher bulk viscosity constant, you get higher amount of focusing right in the depth of the melting region. But when you have lower bulk viscosity constant, there's not much focusing here. Everything is just mainly buoyancy rising and hitting this cold, strong lithosphere. So I've mentioned at the very beginning of the talk that one of the important things that is being observed at mid-ocean ridge is the crustal thickness. So one of the things that we can get out of our models to compare to geophysical observation is the crustal thickness. So here I'm showing you time series of crustal thickness from total melt production. So if I were to take all the melt that's being produced over time, that will give me the total amount of crust over time that can be formed. So for the dashed lines are for the higher bulk viscosity constant, and then the solid lines are for lower bulk viscosity constants. So you can see this transient, and then they pretty much evolve to kind of pseudo-steady state. But this is just to show you what they actually look like, because that's not a thick brush. It's just a very squiggly line. And so when you take the average of of the time series, we can plot this over what I was showing before in terms of crustal thickness versus half-spanning rate. So previously, I showed you the black squares, which is what is commonly used to compare crustal thickness versus half-spanning rate. It's great work by White et al., 2001. And the gray circles are a more recent seismic compilation of crustal thicknesses versus half-spanning rate. So those are all observations. And the colored square, triangle, and circles are from the models. So the squares are from, so what I didn't really tell you is, oh, what was that? So the squares are, oh gosh, yeah, that's horrifying. Make sure there's no earthquake here, that's scary. So the squares are the maximum amount of crustal thickness you can expect if you were to solve for a single phase flow. And the triangles are what you get when you solve for a two-phase flow, and but from the total amount of melt. And then the circles are what you actually get out of the ridge axis. So the difference between the triangles and the circles are pretty much what freezes into the lithosphere. And the triangles that's filled are for for a higher bulk viscosity constant, and the open shapes are for bulk viscosity equals to 1. So the ones on the left. So you can see here, overall, our models fit okay with the observations, so that's good. But we also didn't try to do slower spanning rates because those are incredibly hard. So I'm going to come back to try to convince you of what's going on, what's moving this melt towards the ridge axis to form oceanic crust. So again, there's 3 different pressure on the back of this, the colors on the back of this rectangular box. You have lithostatic pressure, so everything is going up once you create melt. And then you have compaction pressure that's dominant in the melting region. And then you have dynamic pressure, which really only matters in a very small region in a ridge axis. So really what is focusing the melt in most part of the melting domain at mid-ocean ridges is this compaction pressure. And again, I show you this to show you the melt segregation is due to pressure gradients. So to convince you further, remember I had two sets of models, one with lower bulk viscosity constant and one with higher bulk viscosity constant. And so the solid lines here are the compaction pressure gradient taken at 50 kilometers across all the different models. So the solid lines are for the ones with lower bulk viscosity constant, so the set that was on the left. And then these dashed lines are for the set on the right with higher bulk viscosity constants. So it's clear here that your pressure gradient, it's much larger in magnitude for the one that's higher in bulk viscosity constant. And that's also where you see all the melt being focused deep in this melting region. So instead of all just buoyantly rising and then hitting this cold, strong lithosphere like Connor mentioned, it's focusing even deeper than that. So I hope I've convinced you that there's this new focusing mechanism that it's not generally being used because it's hard to do two-phase flow modeling. So what we see here is this melting pressure focusing that's deep, and then you have ridge suction close to ridge, and then decompression layer. So it's very straightforward. It's actually a very straightforward thing as to how this works. So you have Darcy equation again, and then you have conservation of mass, of solid mass. And so if you look at the models itself, it's pretty steady. And so at quasi-steady state, you get rid of the time evolution of porosity. And what you're left with is this part here. And so when you substitute in the compaction pressure definition, you really see that the compaction pressure is really due to the melting rates and the bulk viscosity. So that is really what's determining this focusing mechanism. So to try to quantify how much melt focusing is being, is present in either of the models, decompression layer versus melt pressure focusing, I pretty much take a profile at 5 kilometers depth across all the models. And then you can see this little blimp on the side. And those are all the melt that's coming in because of compaction pressure. And then anything that's in this peak is because of melting pressure focusing. And so what you can see when I plot the average of those is that for the higher bulk viscosity constants, melt is dominantly focused by this melting pressure focusing. Whereas for a lower bulk viscosity constant, you have a switch after about 3 centimeters per year of which one is more dominant. So what does it matter, right? Like, why do we care? How does this actually work, especially compared to geophysical observations? Ooh. So this is the magnetotelluric survey that's done at East Pacific Rise. So they see a wide melt, highly conductive region beneath mid-oceanic ridge, and it's interpreted as melt. So when you overlay, let's say, a 4 centimeters per year or even an 8 centimeters per year model, you see that, yeah, we do see that, high central melt region, that's good. But it's really obvious that something is missing here. We don't really see all that melt in the decompression layer. And so is that a problem with like the MT-EM surveys, or is there something wrong with the models? So that's something I'm trying to figure out with Steve Constable, who's an EM person at Scripps. So all this magnetotelluric data is very sensitive to highly conductive regions. So when it sees high melt region in the center, it wants to place it there. And so to do that, it needs to have a resistive layer on the side. So maybe this layer is just not thick enough for the EM survey to pick up. Or maybe it's just, if you look at the where they place their instruments, it's higher in the center. It's lower on the sides. So that's something that I'm trying to figure out. And the geochemical implications is that really, if you have high degree melt in the center, which you expect because of high upwelling rates, you get depleted in incompatible elements like titanium oxide, things like that. And so if most of that is coming out to make the oceanic crust, that's kind of the signature you expect. But of course, there's also crustal formation too that I'm not taking into account. But then away from the ridge axis, you have low degree melts. So you expect that anything that's off-axis melt that comes out, you expect it to have this signature of being enriched in incompatible elements. So these are kind of my conclusions. We see this melting pressure focusing mechanism, and it's actually very simple. If you look at the equations, it's just compaction pressure is equal to melting rate scaled by bulk viscosity when it's quasi-steady state. And the melting pressure, ignore that line. I'm sorry, that's not right. And so the geophysical observations, it's very important to try to reconcile the modeling efforts with both geophysical methods and geochemical observations. So hopefully we can do that at some point. So that's what I plan to do as ongoing work in this matter. And also I didn't really talk more about the problem, but there's a lot of improvement that can be made. And when I first got into this, what really interests me about this geodynamics is early Earth problems. But when I started working on this, I realized that we don't really understand how the modern day mid-oceanic ridge really works. So that's why I started working on a modern day mid-oceanic ridge before eventually, hopefully at some point down the line, I'll get to study early Earth, plate pulling apart kind of situations. And of course, applying two-phase flow in other settings like subduction zones, which is really exciting because I'm going to briefly touch on it. So this is what kind of work that I'm doing here. I just have a few slides on it. This shows, kind of the carbon cycle at a subduction zone based on illustration by Craig Manning. So you have carbon in sediment and in organic matter and carbonate minerals that's like subducting down. And this carbon, when you get a subducting plate, it changes in heat and pressure, and that gets released and somehow make it to as carbon dioxide in volcanic gases. So as you can, starting off with mid-oceanic ridges is kind of nice because it's a simpler system. But when it comes to a place like subduction zones where you have natural hazards like earthquakes and volcanoes, it's very important to understand how these volatiles work, because those volatiles can potentially affect, the amount of earthquakes. Maybe there's been a number of studies that links water with the devolatilization of a slab to earthquakes and things like that, and also the amount of the kind of magma that you expect at volcanic eruptions. So really what I'm trying to, simple questions here is how much carbon is coming out and how much is going in? And I'm going to use two-phase flow modeling to figure that out. So this is important, like I said, for natural hazards like earthquakes and volcanic eruptions, and it's also long-term, which I'm interested in because early Earth. So this is a recent paper by Megan Duncan and Rashjit Dasgupta. That's always a difficult name. So it's the rise of Earth's atmospheric oxygen controlled by efficient subduction of organic carbon. So maybe over time, the subduction efficiency has changed. And that's really interesting because it affects things like that and how you get life. That's incredible. So one of the first things I need to do is to figure out the carbon solubilities at subduction zones. So I'm working with models from Peter Van Kecken to understand, okay, you have a domain of a subducting slab, and you have pressure and temperature across the board. What is the Gibbs free energy for the 7 calcite reaction equations for all the pressure given the pressure temperature in this domain? And then getting the density and dielectric properties of water at that pressure and temperature, then using the Gutenberg equation, which is a simplification of the Debye-Huckel equation to get an A parameter. And then the goal is to get the 7 equilibrium constants. I'm very close to it, just checking numbers, so I don't really have anything to show you in terms of what it looks like. But really, the goal is to get at two-phase flow at subduction zone to try to figure out. So this is a figure from Kian at DTM, paper published in 2014 that shows this two-phase flow method applied at subduction zone. And the bottom row is with compaction, and the top is zero compaction assumption. So the goal is really to apply to figure out the carbon fluxes at this at subduction zone, and hopefully I'll give you an answer by the end of my tenure here. Hopefully, yeah. Thank you.
Thanks, Joyce. That was super. If you have questions, Kelvin.
There may be an interesting constraint in spreading, and that's the gravity anomaly. Right. Is in fast spreading.
Mm-hmm.
And that would be interesting to see if
Right, and is there an understanding on what those gravity anomalies are from, so that I can better understand how they'll fit in with the models? Right, but they don't really understand why, or I guess that's what the models are for. So maybe I'll figure out and let you know. Sure. Yeah, that's a really good point. I haven't looked at that. Yeah. I don't know.
Yeah. If you could go back to your slide that had the flow velocities, the horizontal flow.
Wow, you remember the slide number? That's amazing. Is that this?
So if I'm the top right there, is that, am I reading it correctly that the ones in sort of the lighter, the pinkish kind of colors are moving?
Yes. So red is kind of moving out to the.
I'm curious about the fate of that melt. Is it flowing at the same speed as
Pretty much.
So is that the fate of that actually just to
Well, I don't know whether it gets frozen because it just leaves the domain, and then at some point it will encounter some, the solidus, or well, the liquidus in this case, before it starts freezing back in. But everything just leaves the domain, and that's it.
And give a sense of the proportion of melt from the system that goes.
It's about, when you look at the, so that's a great question. It's this percentage, right? It's this amount of melt, pretty much. So this is the total amount of crustal thickness you expect if you take all the melt that's been produced over time. And the circles are the melt that's actually coming out of the ridge axis from the top of the boundary to form oceanic crust. So the difference between them is what's being frozen in.
That's
so,
that's a third.
I know, it's quite a lot. Yeah, yeah, it's quite a lot. But you have to also remember that the freezing here is arbitrary, so I could freeze in more. But the point here is that this is the most amount that you can get out of it, out of the models. I could freeze less, and then, get more crustal thickness out of the.
Right, I guess, but the where it go, whether it freezes or not, I guess, is less important than does it reach the axis or not.
Right. You're saying, what about the melt that goes to off that doesn't reach the side versus like the amount that's in the center? I'm not sure, because the thing is that there's been a lot of interest in melt beneath the LAB that's far away from the axis, right? And that's been a lot of, whenever people show this kind of models, that's been the main interest of what happens to those melt. As modelers, I can only tell you that there's melt there. It could come out as off-axis volcanism, or it can freeze in. We should look at the Mantle periodites, go dredge some more. That would be really great. I'd love to know.
They won't be exposed there.
I know, exactly.
You showed these illustrations early on about you don't have to show me, showing the grains of olivine and the porosity around them and the fluid going between them. So how much do your results depend on assumptions of what the grain size distribution is?
A lot.
Are there any constraints on this?
Well, there are some constraints. I mean, we definitely assume a grain size, and we assume background permeability based on these experiments. Because really, I mean, I can write it down because it makes more sense. So pretty much our permeability K is equals to something like, your K naught, phi naught, N, and phi N. So it has a huge dependence on porosity. I mean, you can tell here, when you increase melt, you're going to have a higher permeability. But it also depends on your what you assume to be K naught, which is based on grain size and things like that. So yeah, there's an inherent assumption there. And I wish we knew more.
Right.
There needs to be more experiments, but these experiments are incredibly hard to do. Wait, can you repeat that? Sorry. Yeah, I mean, viscosity is based on pressure, temperature, strain rate. And it has a little bit of yield criterion right at the ridge axis to make sure it's weak enough. Right, so you're saying in terms of viscosity, right? Yeah, yeah, right. So you're talking about like what I use for, let's say, the non-dimensional adiabatic gradient, Right, yeah. This is only 100 kilometers, yeah. Yeah. Mm-hmm. Right, so maybe there's some capillary effect or, yeah, there's no.
There's always a viscous boundary. So at what point does the boundary layer dominate the fluid flow? What point does the viscosity?
Right. Can you repeat the last part of the, sorry.
I have the scales all wrong.
Oh, I see. Right, so really, really from here to here.
Yeah, so,
right.
And that's what struck me when I saw these figures.
Right, I guess that's why the permeability really depends on the porosity, right? So, right, yes, exactly. It's the melt volume fraction. So in all my models, I mean, I'm pretty much trying to parameterize all of this, right? Because I'm not technically solving for this fluid flow. It's that would be a little bit intensive work. Yeah. So yeah, I agree. It's that's actually parameterized by that, right? So.
That's just interesting. I mean, I understand.
Yeah.
At the same token, Larry's point is well taken.
Absolutely.
This is where the action.
Yep. This is.
Environmental point of view.
It's a really hard experiment. If you listen to Wenlu Ju at Maryland, I don't know whether she's been here to give a talk. Maybe she should. That would be great. Yeah, I mean, like the experiments that they do take a long time, and it's just incredible that they're even able to do that. So I really appreciate it when they give me some numbers to work with at least. If not, I don't know what I'm gonna do. I can just guess, edit, and try to constrain it from, okay, this doesn't make sense, this makes sense, and go with that. But at least we have some constraint here. Like the exponent on porosity, n, it's between 2 and 3. Somewhere there. At least it's between 2 and 3 and not 2 and 30 or 300, So I'm very thankful for that.
So in a fast spreading ridge, you typically have a ephemeral or somewhat persistent. Is that something that's going to affect the flow field? I mean, I would imagine.
So when you say...
Like in these specific rides, you have an axial magma lens in there that they're not existent.
So when you say a magma lens, you mean right in the crustal, right in the crust, right? So the top of my boundary is the moho. I don't care about anything I'm not trying to model anything that's in a crust because it's brittle. It's not, viscously deforming like what's happening down here. So the melt comes out, forms the crust. What happens to it? I can't tell you what's going on with it.
So while you have that up there, it's also very interesting the amount of melt. Jesse's question. A lot of off-axis volcanism in these specific rocks.
Yes.
It's very spotty. Volcanic production melt is
right.
Yet it's not a very persistent.
Right. I mean, that depends on how the off-axis melt would actually come up, right, to actually form off-axis little seamounts and stuff.
So these guys have sources that are kind of below them.
Right. You mean?
This here has sources kind of way off axis, right?
Yeah.
They never see the center.
No.
At all.
Yeah, so maybe someone can tell me off-axis melting, what's the geochemical signatures? Because I would say that there would be, you know, I know.
Higher water.
Yep.
All that stuff. You expect.
So that's actually what's observed.
Yeah. Oh yeah.
So that's good. That's good for the models. I'm happy with that.
No, that
I'll take
well.
that.
It doesn't fit quite as much as the persistence to me.
Yeah, it takes, I mean, it's not that easy to get through here and also get through the brittle crust, right? And a lot of this, when it gets encountered a cold-strong lithosphere, is going to freeze. So I would expect that most of it actually freeze, even though you see quite a lot of melt here. A lot of it is going to freeze, and some of it, you need to have enough melt for it to actually escape and form, you know, some off-axis volcanism, right?
But it's always lower extensive melting.
I'll take that. I'll take that. Right. Yeah, so all the seals and whatever that's like in off-axis melting.
Is there less off-axis volcanism